Today's session is about Lagrange's linear partial differential equation part 2. In previous section, we had discussed two methods of solving the auxiliary equation given case 1 and case 2. Today we will be discussing case 3, method of multipliers making new fraction in AE. If one pair is integrable, we have to pick that pair, integrate it and find solution 1. And to get solution 2, we have to create new fraction by method of multiplier. If none of the pair is integrable, then we have to create two new fractions. Creating new fractions. So to existing auxiliary equation, we have to we have to multiply it with a set of multiplier like L, M, N, and we get this fraction, that is L into dx is equal to L dx, M into dy is equal to M dy, N is equal to dz is N dz, L into P is LP plus MQ plus NQ. Here this is a new fraction, and this new fraction is always equal to the existing fraction. So here we have to try to choose the multiplier in such a way that the denominator of the new fraction, that is LP plus MQ plus NR, will be preferably 0. This we do it for ease of integration. Let's see an example. Here we'll take this example. We'll name this equation as equation 1. Now we have to we'll change it in this format. So dx by P is coefficient of P, which is x. Then dy by capital Q, dy by coefficient of P, which is minus y, and similarly dz by y, dz is equal to y square minus x square. Now taking fraction 1 and 2, we get this. On integrating, we get log x is equal to minus log y plus log c. Log c1 is the integral constant. Bring this here, we get this. Now using log property, we get this, and this log and this log will get cancelled. We get this. This is solution 1. Now we'll take fraction 1 and 3. When we take fraction 1 and 3, here it is given dx and dz. So the terms, everything should be in terms of x and z. But here we see y, which cannot be cancelled. So this becomes difficult to integrate. Similarly, when we take fraction 2 and 3, here because of the presence of y square, it becomes non-integrable. So we have to use the multipliers to form new ratio. So here we are using the multiplier xy 1. So the multiplier we can use of our choice. So commonly used multiplier are these. So let's continue. So multiplying x dx is x, dx is x dx plus y dy is y dy plus 1 dz is dz. The denominator x into x is x square. Here y minus y is minus y square plus here 1 into y square is y square, 1 into x square is x square. So when we simplify it, it gets cancelled, it becomes 0. So these are the this is the new fraction. So now we get altogether 4 fractions. Here 3 was already there, and this is a new fraction. Now when we take fraction 1 and fraction 4, this 0, when we multiply with this, when it goes here, this whole term becomes 0. So we get this. On integrating this, integration of c is a constant, we can call it as c2, and integration of x is x square by 2 plus y will be y square by 2, and dz will be z. So here we have to take LCM, and then we can get rid of 2. So we get c2, which is a constant, is equal to x square plus y square plus 2z. So general solution will be psi of xy, which is solution 1, and x square plus 2y square plus 2z, which is solution 2. So this is the general solution required. Now we'll take second example. Let this be the equation. We call it equation 1. We have to change it into this format. So dx by coefficient of p is this, is equal to dy by coefficient of this is equal to dz by xy minus zx. This we'll call it as equation 2. Now we'll take the fraction 2 and fraction 3. So this is fraction 2 and fraction 3. Here x is common, so we'll take the x and it will get cancelled. So we'll be left with dy by y plus z is equal to dz by y minus z. So bring this here, bring this here. So we get this. Okay, multiply this by y and this. Multiplying, we get y dy minus z dy is equal to y dz plus z dz. Now bring this z dz here and bring this z dy here. We get this. On integrating both sides, this y will become y square by 2 minus this z will become z square by 2. Integration of y dy is y is constant and dz will be dz plus here z is constant, integration of dy will be y. So simplifying it, we get this. Bring this to y, 2yz this side. So we get this and this is, and here 2c is there. We can call it as, this is also constant. We can call it as another constant as c1. So this is our required solution. Now we got solution 1. Now we have to find solution 2. So we have to take another pair to integrate. But here none of the other pair is integrable. So we have to make a new fraction or new ratio by taking a multiplier. Here we are taking x, y, z as a multiplier. So now we have to form the new ratio. So x into dx is x dx plus y into dy is y dy plus z into dz is y dz. Similarly, we have to multiply with this with the denominator also. X into this term will be this after multiplying plus y into this term will be this after multiplying with y and z into this term is this. Now after simplifying, this and this will get cancelled, this and this will get cancelled and this will get cancelled and finally denominator will be 0. So now we have 4 ratios. These are the three original ratio and this is newly formed ratio. So when we take two fraction, any two fraction, when we multiply with 0, it becomes 0. So we get this. So integrating this on both the side, 0 when integrated we'll get a constant. So we'll take it as C2 by 2 for ease of calculation. Now x square dx on integration become x square by 2 plus y square dy will become y square by 2 plus z square dz will become z square by 2. Now here in bottom all the 2's can get cancelled. So we get C2 is equal to x square plus y square plus z square. This is solution 2. So here the general solution phi is equal to general solution phi is a function of solution 1 and solution 2. Solution 1 we have calculated earlier, which is y square by 2 minus z square by 2 minus 2 yz. And now this is the second solution. Second solution is x square plus y square plus z square. Now let's understand another example. Let this be equation and now we are going to change here this into Lagrange's auxiliary equation. So dx by coefficient of p is this is equal to dy by coefficient of q is this is equal to dz by this value, and we'll call it as equation 2. Now when we see this here, when we take fraction 1 and 2, here this is in dx, this is dx and this is dy. So here the term z we have to try to eliminate it, but here it is not possible to eliminate it. So these two fraction cannot be integrated. Similarly, when we take fraction 2 and fraction 3, here dy and dz is there. So this x term will become difficult to integrate, and it cannot be cancelled also. So these two, it will here integration is not possible. Similarly, the other combination, this one and 1, there is a fraction 1 and fraction 3, again it is difficult to integrate. So now we'll be making new ratio or new fraction will be forming by using multiplier x, y, z. Okay, so x into dx is x dx, y into dy is y dy, z into dz is z dz. and x into this term. So it becomes xmz minus n xny plus y into this term will become this, plus z into this term becomes this. When we simplify this, here it becomes 0. Now we have 4 ratios. These three are original ratios and this is newly formed ratio. So whenever we take fourth ratio with any of the other ratio, that term will become 0, because this 0 when goes there becomes 0. So we get here 0 is equal to x dx plus y dy plus z dz. Now on integrating it, we get integration of 0, we will keep it as c1 by 2. It's constant, so we'll keep here c1, or we can just put 2 also. The 2 is also constant for ease of computation. And this will become x square by 2 plus this will become y square by 2 plus z. This will become z square by 2, and all these 2 can get cancelled, and we get c1 is equal to x square plus y square plus z square. This is the solution. Now this is solution 1. Now we have to get another solution. For that we have to use new multiplier. Now we will take it as lm and n, lm and n. So multiplying this with l becomes l dx m dy plus n dz divided by denominator will become this when we multiply denominator with this. So now when we simplify it, denominator becomes 0. The 4 ratios will be this original and this is the fourth one is a new ratio. So when we multiply, when we bring this 0 here, the term will become 0. We get this. Now on integrating it, we'll keep 0, when integration of 0 will be c, and this term will become I dx will become ix plus m dy will become my plus n dz. Integration of z is z, so it becomes nz. So we get this, which is solution 2. Hence general solution 5 will be equal to solution 1 comma solution 2. So solution 1 is x square plus y square plus z square, comma, and solution 2 is lx plus my plus nz. In last two examples, we had seen that one of the pair of fractions were integrable and another new pair we had created for getting another solution. But here in this solution, we'll be seeing what will happen if none of the pair is integrable. Okay, let's see. Let's take this equation. We'll call it as equation 1. Now we'll change it into Lagrange's auxiliary equation, that is dx is equal to coefficient of p, which is this, dy by coefficient of q, which is this, and dz by this expression. So we'll call this equation as equation 2. When we see here, when we compare fraction 1 and fraction 2, here this is not integrable, because here it is dx and here dy, and here this term z cannot be eliminated. So with this term it becomes difficult to integrate. Similarly, when we compare this equation, this fraction and this fraction, here this x term, it cannot be eliminated, so it becomes difficult to integrate. Now we'll take fraction 1 and fraction 3. Here again, this is dx and this is dz. So here term y becomes difficult to integrate, and it is not cancelable also. So none of the fraction here is integrable. Now we have to find new ratio by using multipliers. So in this case we'll be using multiplier 1 by z, 1 by x, 1 by y, and 1 by z. So multiplying this here 1 by x with this term, we'll get this, plus 1 by y into dy and 1 by z into dz. Similarly, we'll be multiplying this in denominator also. 1 by x into this term. So x and x will get cancelled here. We'll get so we'll get here 1 by 1 will get cancelled here, and we'll get only this, minus 1 by y into this term. So here again minus this. So 1 by y will get cancelled here, see. And only this term will be left. Plus 1 by z into this will get this term. Here z and z will cancel. On simplification, all the terms will get cancelled and denominator will become 0. So when denominator is 0, then we get this expression. 0 is equal to this value here, 1 by x dx plus 1 by y dy plus 1 by z dz is equal to 0. On integrating this, so integration of 1 by x is log x plus integration of 1 by y is log y plus integration of 1 by z is 1 log z is equal to integration of 0 is constant c1, but for ease of calculation we will take the constant as log c1. Now this is using log property, we'll get log xyz is equal to log c1. This log and this log will get cancelled, we'll get xyz is equal to c1, which is solution 1. Now we have to get a second solution, so we'll have to make another new fraction because none of the pair is integrable. So here we'll take, to make new fraction, we'll make the use of this multiplier x, y and minus 1. So multiplying this with the auxiliary equation, we get x dz plus y dy minus dz. Here minus 1 is there, so minus 1 into dz is minus dz. And similarly denominator also will be multiplying, we'll get this. When simplifying this, it becomes 0. So whenever we get 0 as a denominator, then we get expression like, we'll get expression like this. So x dx plus y dy minus dz is equal to 0. Now on integrating it, the x becomes, on integration, x square by 2 plus y dy becomes y square by 2 minus integration of dz is minus z. And this integration of 0 is constant, we'll call it as C2. So this is the required solution 2. So general solution 5 will be the function of solution 1 and solution 2. Solution 1 was xyz and solution 2 is this. So this is the required solution. Let's see next example. So we'll let this be equation 1. We'll convert it in the form of Lagrange's auxiliary equation, that is dx by coefficient of p is equal to dy by coefficient of q is equal to dz by x plus y. So we'll call this as equation 2. Now here none of the pair in this fraction, none of the pair of the fractions in this equation is integrable. So we'll have to make new set of fractions by using method of multipliers. First we'll take the multiplier 1, minus 1 and 0 and we'll try to make fraction. So 1 into dx is dx, minus 1 into dy is minus dy, plus 0 into dz is 0. And 1 into y plus z is y plus z, minus 1 into z plus x is minus z minus x, 0 into this is 0. On simplifying, we get minus of x minus y. We'll call this fraction as fraction 3. Now let's make another fraction. Let's take 0, 1 and minus 1 as a multiplier. So 0 into this will be 0 plus 1 into dy is dy. Here minus 1 into minus 1 into dz is minus dz, divided by 0 into this term will become 0, 1 into this term will be z plus x, and minus 1 into this term will be minus x minus y. So here x and x will get cancelled, we'll get z plus y. We'll take minus out, so we'll get y minus z. We'll call this as fraction number 4. We'll make another fraction. Now this time multiplier will take as 1, 1, 1. So we'll get 1 into dx is dx, 1 into dy is dy, plus 1 into dz is dz, and numerator 1 into x plus y, 1 into y plus z is y plus z, plus 1 into z plus x is z plus x, plus 1 into x plus y is x plus y. So simplifying it, we get 2 times x plus y plus z. Now now we are from third, fourth and fifth fraction are newly formed ratios or newly formed fractions. So these are this. Now here we take d out, so we'll get x minus y, and by minus of x minus y is equal to, here again d will take it out, we'll get this, and here again d we are taking it out, so will get this. Now these are the three newly formed fractions. Now taking fraction 3 and fraction 4. So this is fraction 3 and this is fraction 4. When we integrate, so here actually this minus and this minus will get cancelled, and on integration of this, it is log x minus y is equal to log y minus z plus log plus c. When we integrate, we have to have one constant, so one arbitrary constant. We'll keep it as c, or we can keep it as log c also. So this is constant. Now bring this here, so we'll get here log x minus y minus log y minus z is equal to this log c. So log property, using log property, we'll get log of x minus y by y minus z. This is a written typo, is equal to log c1. So this and this will get, this log and this log will get cancelled. Then we'll get x minus y by y minus z is equal to c1. This is solution 1. Now we'll take fraction 3 and 5. So this is fraction 3 and this is fraction 5. So this 2 we can bring it here. So we'll get this. Okay. Now bring this term here and this y. Now integration of this is log x plus y plus z, plus this 2 will be out as a constant, and integration of this will be log x minus y, plus we have to keep an arbitrary constant. Now when we just see this due to log, because of log property, it can be written as log x minus y to the power 2. Now taking these two, using log property here addition, so it can be written as log x plus y plus z into x minus y plus x minus y whole square, plus this log c is here. Now bring this log c to the other side, and then cancel this log and this log. We'll get x plus y plus z into x minus y whole square is equal to c2, which is solution 2. Now we have got solution 1 and solution 2. So general solution will be phi of solution 1, which is x minus y, y minus z, comma, and solution 2, which is x plus y plus z into x minus y whole square. Now in this case, here case 4. Case 4 is used when case 1, case 2 and case 3 are not applicable. Case 4 is used when case 1, case 2 and case 3 is not applicable to derived solution. Then we make new fraction creating other method. So let's take an example here. Solve this equation. Let's take an example. Let this be the equation. We'll call it equation 1. So we'll bring it into Lagrange's auxiliary equation form. So dx by coefficient of this is equal to dy by coefficient of this is equal to dz by z. So we'll call this as equation 2. Now since all these three fractions, their pair are not integrable, we have to make new fractions. So first we'll make new fraction by adding 1 and 2. When we add this and this, we get dx plus dy is equal to cos x plus y plus sin x plus y. So we'll get this. Okay, so this will be our fourth fraction, and we'll make one more fraction by subtracting 1 and 2. When we subtract 1 and 2, this dx minus dy will get dx minus dy, and here cos x plus y minus sin x plus y. So we'll call this as fraction 5. So we got all the first, these are the three fractions which was the original fraction, and these are the two newly created fractions. Now taking fraction 4 and 5, we're taking this. Now keep this here and bring this here. So we get dx minus dy is equal to cos x plus y minus sin x plus y divided by cos x plus y plus sin x plus y into this term is there. So we'll write it like this, and we'll call this equation as equation 4. Now let's consider cos x plus y plus sin x plus y as t. And when we differentiate this, we get minus sin x plus y plus cos x plus y into dx plus dy is equal to dt. So we got dt and dt. So substituting this here. So this will become dx minus dy, here it is, and this term will become dt, and this is t. So we get this. On integrating this, dx will become minus, so dx will become x minus dy will become minus y is equal to dt by dt. Dt by t is log t plus or minus any arbitrary constant. Here we are taking minus arbitrary constant. It can be anything, any constant. So we get this. Now here we are substituting the value of t here, putting back the value of t. So we get log, and this t value we are putting here, minus log c, which is arbitrary constant. Now here this, here log this minus log this. So according to log property, it will be log this value cos x plus y plus sin x plus y by c. Now this x minus y and this log term, it is like this, and it can be converted into exponential form like this. So converting it into exponential form, we'll get this c1, we can bring it here. So c1 will write it and then convert rest into exponential form. We get e x minus y is equal to cos x plus y plus sin x plus y. So we get this, and bring this here to the other side. So it will become divided by this, or when we take it up, it will become minus x minus y. So this is solution 1. Now we have to create next one more. We have to solve for one more solution. So we'll take fraction 3 and 4. So fraction 3 and this is fraction 4. So we are taking fraction 3 and 4 like this. Dividing and multiplying by 1 by root 2 here. So we'll get dz by z is equal to 1 by 2 here and 1 by 2 here. And here 1 by, we know that sin pi by 4 is equal to 1 by root 2, and cos 1 by 4 is also is equal to 1 by root 2. So instead of 1 by root 2, we will be in the place of 1 by root 2, we will be putting sin pi by 4 and cos pi by 4. So now when we put this, it is in the form of sin a plus b. So we'll write it here, sin pi by 4 plus x plus b. That is, this is in the form of sin a plus b. Okay. Now we got 2 root z by, dz by z is equal to dx plus dy by this sin a plus b, which is in the form of sin a plus b, that is sin pi by 4 plus x plus y, can be written as 1 by sine can be written as cosecant. So we are writing it as cosecant pi by 4 plus x plus y. And this dx by dy is written here as such. Now let us consider pi by 4 plus x plus y as t. On differentiating it, we get dx plus dy is equal to dt. Now put the value of t and dt in this equation. So we get root 2 dz by z is equal to cosecant. This is t and this is dt. So integrating this, integration of this and integrating this. So integration of root 2 dz by z is root 2 is constant, we'll keep it as such, and dz by z is log z is equal to integration of cosecant t is log tan t by 2, and then we have to add one arbitrary constant, so we'll keep it as log c2. Now this means here we'll have 2 root 2 is there, log z is log z, and this one, this log term and this log, due to log property, it will become log tan t by 2 into c2. Okay, now we got this. So here now we'll be putting the value of t. So here it is, and this log next another log property is this root 2 can be brought here as log z to the power root 2. Okay, so log z to the power root 2 is equal to log tan, here t value we have substituted, we get this into c2. Now here this log and this log will get cancelled. Z root 2 is equal to tan x plus y plus pi by 4 by 2 into c2. Now bring this tan term here. When it comes here, it will become 1 by cot. So we get z to the power root 2 into cot of this term is equal to c2. So this we'll call it as solution 2. Hence general solution is phi of solution 1, which is cos x plus y plus sin x plus y into e to the power minus x minus y, and solution 2, which is z to the power root 2 cot x plus y plus pi by 4 divided by 2 is equal to 0. So this is our required solution.